Thank you. Thank you. Good afternoon, Unite Seoul. Second day, afternoon, just after lunch. I hope no one is sleepy. So, thank you for coming to this talk. My name is Ian, as you've just heard. I am a developer relations engineer on Unity's enterprise support team. That means that I visit our largest customers and I help them resolve tough issues so they can get their games shipped on time and performing well. Now today, we are going to talk about Unity's Scriptable Object class. I'm going to introduce what it is and how to use it. But mostly, we're going to focus on the various ways you can use scriptable objects to simplify your life as a developer. So to start, what is a scriptable object? To be very brief, it's a class that derives from the Unity Engine.Object class. Talk done. Okay, so Unity's serialization system can read and write from the scriptable objects fields, or member variables if you come from a C++ background. Also, Unity understands and keeps track of the references both to and from a scriptable object. If this sounds simple, that's because it is. Scriptable object is a simple class with a simple API, and that's a good thing. You see, simplicity is something that we should strive for when we're developing systems. But it may be easier to understand scriptable object if we understand what it isn't. So we're going to compare it to something that every Unity developer is familiar with: MonoBehaviour. What is a MonoBehaviour? Again, a very simple answer. It's a script. But you might also note that MonoBehaviors receive callbacks from the Unity engine. Start, update, on collision enter, etc. A MonoBehaviour must always be attached to a game object while it's alive. If you create one at runtime, you use the add_component API, which requires you to attach it to a game object, right? MonoBehaviors are compatible with Unity's serialization system, so we can save them. When we do save a MonoBehaviour, its data goes into a scene or into a prefab. Now let's compare these ideas to Scriptable Object. Can you spot the differences? I have highlighted them in green on this slide, which is not the easiest to read, but just like a MonoBehaviour, a Scriptable Object is a script. It's in the name, Scriptable Object. It's also compatible with Unity's serialization system. However, it doesn't receive most callbacks from the Unity engine. If you put an update function on a scriptable object, it will not be called. At least, it will not be called automatically by Unity. You are free to call it yourself. Also, you can't attach scriptable objects to game objects. Scriptable objects lead independent lives. And finally, each scriptable object's data is saved into an asset file. Well, let's talk about these files a little bit more. When we are saving MonoBehaviours, they are always saved alongside other kinds of objects. The simplest prefab that you can make that contains a MonoBehaviour will actually contain 3 different objects, at least. The MonoBehaviour itself, the game object to which the MonoBehaviour is attached, and the transform that is attached to that game object. All game objects have transforms, remember. Okay, so if you add more MonoBehaviors or other components like a rigid body or animator, then all of those values will have their data saved into the same prefab file. If you tweak values on just one of the components on a prefab, you have changed that prefab's file. If your project is under version control, and I hope it is under version control, then you do have to hope that no one else on your team has touched the same prefab or scene, because everything I have just said also applies to scenes. Now, in contrast, every scriptable object can live in its own file, so they're much friendlier to version control systems. Compared to prefabs and scenes, it is now much easier to avoid merge conflicts if you use scriptable objects to hold your data. Okay, enough talk, let's have an example. We're going to pretend we're making a game. Our game will have NPCs. Like any good game, we want to kill our NPCs. So we might make a simple MonoBehaviour to handle our health and AI systems, something like this. If you look in the inspector UI in the editor, we'll have something to make our designers' lives easier. So you can tweak enemies' health, tweak their AI. You know, it's easy for them to change our levels. So the class we create might look like this. We'll have two integer variables. One indicates the NPC's maximum amount of health, and another tracks its current health. Now you should note that the current health is not serialized. That's so we don't save it out with the rest of our information. We only need it when the game is running. We'll also have another integer in the middle there, which tells our AI system when the AI should switch between healthy and hurt states. And two other variables to describe what the AI's behavior should be when healthy or hurt. Very simple. Well, there's already some problems. First, if we want to tweak the maximum health of some NPC, we have to tell everyone else on our team not to touch that NPC's prefab, or the scene the NPC is in if we are not using prefabs. If we want to change every NPC's maximum health, we have to go through all of them by hand. Or we write a script, which is almost as inconvenient. And what happens if someone just accidentally changes the value for one NPC's maximum health? Now that one NPC might be a lot stronger than all the others, and we have to go rely on our testers to catch that error for us. Or we write some tools to check all of our content. That's a lot of work. So let's refactor this system. We're going to separate our design data from our runtime data. You can call this separating the shared state from the non-shared state, the data shared between many NPCs and the data unique to each specific NPC. So as you can see, I have removed all the maximum health and AI-related information from my MonoBehaviour, and I have left only the non-serialized current health field. Generally, we want that to be specific to every individual NPC. The rest of the information I've placed into this NPC health config object. Well, what kind of object is that? This talk is on scriptable objects, so I think you can guess. Yes, a scriptable object. It has all the variables that we've taken from the MonoBehaviour, so it's very simple to create. We've just changed the parent class from MonoBehaviour to ScriptableObject. And sharp-eyed observers will see the Create Asset menu attribute at the top. What does that do? That attribute adds a new item to the Create Asset menu in the Unity editor. When clicked, it creates a new health config object as an asset in my project. So now, it's very easy for me to create new pieces of health config content. So, quick summary. What does our new NPC health config do? It stores all the shared state for our NPCs. Now, our designers create NPC health config objects. Those objects are saved to files in our project. The designers attach those NPC health config objects to define how NPCs' health systems will work. In the inspector, things look very similar to the way they did before, except now the NPC health script has a reference to the NPC health config object. What are the benefits of this setup? First, dearest to my programmer's heart, it cleanly separates our design data from our runtime data. It encourages us, through the structure of the classes themselves, to keep state that needs to be shared between NPCs and saved as content in one object, and to keep the rest of the state elsewhere. But it also makes our designers' lives easier. When tweaking values, they just have to change one health config object. Then, all the NPCs using that health config object will instantly get the updated values. Optionally, you could write a custom property drawer in the Unity editor. This would display any custom data your designers might want when viewing fields of the NPC health config type. But there's more. If your designers are tweaking the health config objects while testing a level in play mode in the editor, then those changes to health config objects will be saved. You will not lose your changes when you exit play mode. It's one of the most requested features in Unity, and it's already there. As an added bonus, in larger projects, adopting this pattern can make it much faster to load your scenes and prefabs. Yeah, you're saying what? Why would moving data to a different class make it faster to load? Well, to explain, let's think about what Unity serializes when saving scenes and prefabs. When we do save a scene or a prefab or any other kind of content, Unity serializes every single thing inside them. In a scene, we will serialize every game object, every component attached to every game object, every serializable field on every component on every game object or MonoBehaviour in the entire scene or prefab. There is no duplicate data checking. There is no compression. We save everything. And when we load that scene or prefab, we have to read through all of those saved properties, all the saved game objects and components. Even if they have the same values, we read all of them. Even if you don't use them, we read all of them. Even in today's world, where everything has a solid-state hard drive, reading from the disk is one of the slowest things you can do. But what happens when we move our data into a single scriptable object? Then the design data is saved once in that scriptable object's asset file. Any MonoBehaviors using it will only serialize a reference to the scriptable object, a single property instead of many. As the amount of shared data that we move into our scriptable objects grows larger, so does the performance benefit. Okay, before we get too deep into the ScriptableObject class, let's review the ScriptableObject API. How do you create a new scriptable object? At runtime, we use the createInstance method. We can call this in the editor as well. While in the editor, we can save an instance of a scriptable object using the asset database API. We can put it into a new asset file by using the createAsset method. If you want to put multiple scriptable objects into one file on disk, then you can use the addObjectToFile method instead. Or, if you just want a simple menu item to create a new asset file with a single instance of a scriptable object in it, you can use the createAsset menu attribute, like I showed you earlier. What callbacks does a scriptable object receive? It's not 0, it's 3. First, easiest to explain, onEnable. It is called when the scriptable object is instantiated or loaded. Now remember, this is a synchronous call. It will execute on the main thread as part of the createInstance call or as part of a load call, such as resources.load or assetBundle.load. In the editor, this is also called when we reload the scripting domain. That's what happens when we finish successfully recompiling your scripts. Okay, the other two. OnDestroy is called right before a scriptable object is destroyed. But it is worth noting that OnDestroy is only called in response to the destroy or destroy immediate APIs. It will execute after the onDisable callback. OnDisable is called when the scriptable object is about to be destroyed, but not just when you call destroy or destroy immediate. It will also be invoked on the main thread by Unity's asset garbage collector if the asset garbage collector is about to unload this scriptable object. We'll talk more about that on the next slide. Also, in the editor, onDisable is called just before we unload the scripting domain in preparation for reloading your recompiled scripts. Okay, so I said earlier that scriptable objects lead simple lives. They are created and loaded just like other assets, like textures, like audio clips. They'll be referenced by something in a scene, or maybe they'll be loaded by an asset bundle or from the resources system. Maybe you'll create them at runtime. While they are alive, they just hang around, letting you use them however you like. Eventually, they will get unloaded. That can happen in two ways. First, when you explicitly tell Unity to unload them. That's the destroy or destroy immediate APIs. Alternately, they will be eliminated by the asset garbage collector if we detect that there's nothing holding a reference to the scriptable object. The asset garbage collector is what runs when you invoke the resources.unloadUnusedAssets API. It also runs when you change scenes. Now, quick note of caution. A lot of people like to think that Unity is a C# engine. This is wrong. Unity is a C++ engine, and it has a C# scripting layer on top. So, just like all the other classes that derive from Unity engine.object, there's two parts to a scriptable object. There's a native C++ part and a C# script part. The C++ part, represented by this, I guess it's red on this screen, the red box, handles the interface with the rest of the Unity engine. It's responsible for serializing your data and for giving the object a unique identity. That is the instance ID, which you may have seen while browsing the Object API. The C# side is just your script. That's this blue box here. You control that completely. Now, let's pretend that someone wrote some C# code somewhere that has a variable somewhere. That variable is a reference to one of your scriptable objects. What happens when we call destroy? Well, immediately we wipe out the C++ part. That's unloaded immediately and completely during the destroy call. But there is no way to force a C# object out of memory. You have to wait for the C# garbage collector to clean it up. It won't do that if you have a reference hanging around somewhere. This is a very common problem. If you destroy a scriptable object and do not release all the references to it, then the C# script part will hang around in memory until those references are gone. Worse, Unity will tell you that the references point to null. It's because Unity has a custom equality comparer that checks to see if the native part of the scriptable object is gone. If it is, it makes the destroyed scriptable object look like null. So make sure you release references before you call destroy on a scriptable object. Okay, let's look at some common patterns for using scriptable objects. This is probably the part you all came here to see. Okay, the first way to use scriptable objects, just a plain old data container. We looked at this earlier. Scriptable objects are a very good way to just hold data, both during development and at runtime. But there's a clever way to use them. Take data that is in a format that is expensive to deserialize, like JSON or XML. You can write a script that converts those files to scriptable objects at build time. That's much faster to load than plain text. But there are much more interesting ways to use scriptable objects than carrying data around. One way to use them is as an enum. But it's an enum that your designers can easily extend. Consider what you usually use an enum for. Comparisons. You check to see if one variable is equal to another. Well, you can do that with scriptable objects too. You can see if two variables refer to the same scriptable object. So, what would this look like? For this example, let's pretend we're making an RPG. Not trying to play to the crowd at all. We're going to implement an item system, and we want to have different kinds of items. We'll determine what kind of item we have based depending on how the player character will equip that item. So, I will create a very simple scriptable object class. This will tell us what the item's visual icon will be. That is a Unity sprite. We'll also have a field that tells us what slot this item will get equipped into. I will add two empty methods, and my other game code will call them as needed. So one that gets called when a character equips an item, and one that we will call when a character removes an item. Simple? Now, what do we put in that game item slot class? Well, right now, we don't need any data, so we just need to compare instances. I've created an empty class that derives from ScriptableObject. And now the slots that our game content supports are just content. Our item types are just content. When we are checking to see if a character already has an item equipped in the same slot, we can loop over the list of equipped items and see if any of them refer to the same slot as the item the character is trying to equip. And now our designers can make up new slots, and our code doesn't have to care. No changes. The designers also get this nice drag and drop UI. You just take the slot and drag it onto the item. Simple. The best part about this, though, is that as our design evolves, we can begin to attach data where it's needed. Maybe we want to have some kinds of items that the player cannot equip. Maybe they should only be equipable by certain character classes. Maybe we're making a giant broadsword that can only be equipped by a knight. Well, since our slots are already scriptable objects, adding that data is simple. We just add it to the game item slot class, and then we implement the code to use the new data. Okay, let's go another step further with this same example. Our items are kind of boring right now. They don't really do anything. Let's make it so that any item has some effect when they get equipped. For example, if your character equips a good sword, they should get strong. So I'm going to adapt the game item class a little bit. I have added an array of game item effect objects. This new class will describe what happens when we equip our item. So we are going to have to put a bunch of code in onEquip and onRemove to handle all those different effects, right? No. Hold that thought. Here is a simple game item effect class. Like before, it is just data. Our effect class tells us which stat to change and how much to change it. Now, we could add some simple code to onEquip and onRemove to apply this effect, to change the character's stats. But should we really do it this way? What happens if the designers want to do something other than add values to stats? What if they want to decrease one stat and increase another? Like we've got a sword that's possessed by a demon or something. Well, if the game item effect class just carries data, we will have to add all the different types of data to that class. And then our game item class will have to implement the code to actually execute all these different effects. That gets messy very fast, and it's very ugly. But why should game item even care about what the effects are doing? Why not put the code for that into game item effect itself? Let's do that. So, we've modified the game item effect class. We've now made it an abstract base class, so we can have many different types of effects. Each of them will carry their own data. But they will present a consistent API to game item. So we can now very easily make a game item effect that performs the add stat effect. Our data here is still just the stat to change and the amount to change it. In our onEquip callback, we will tell the character to add some amount to the stat. We'll do the reverse when removing the item. And we can also easily do more complex things. This is only limited, really, by your imagination and your game. So here is the other effect that I talked about, one that takes points from one stat and moves them over to another stat. I realize that in a real game, you would want to do more checking, make sure the player has enough of one stat before moving it all over to the other stat. But this is a simple example, and that would not fit on my slide. Now, with the help of the Create Asset Menu attribute, it is easy to make instances of these two game item effects. Here's the two we're going to assign to our sword. When equipping it, our character will get a little faster, we will have less defense, and we will get stronger. What does our game item class look like now? It's still very simple. When the item gets equipped, we loop over all the effects and run their onEquip methods. We do the same in onRemove. I've just omitted that detail, but you can imagine it. Our UI is still simple. Our designers now drag and drop effects onto items. With just a little code, we have a functional item effect system. It is not lineage, but it took us 5 minutes. The best part about all of this, we've separated our concerns. Effects care about applying their changes. Game items stay clean. The interface is so clean, you could write automated tests to check it. We've also got an easy UI for our designers, and it's very easy to add new content without refactoring existing classes. We can create new subclasses of game item effect whenever our designers come up with something new. This pattern is actually extremely powerful. We are now using scriptable objects as delegates, and they control the flow of our game logic. These delegates have a simple, polished UI and can easily carry context-specific data with them. With this pattern, it's very easy to make our game logic configurable by our less technical teammates. Imagine an AI system whose different AI behaviors were driven by scriptable objects. Our NPCs, of course, would just be MonoBehaviours. But the AI they execute could be a scriptable object. The MonoBehaviour would tell the scriptable object to execute its logic every frame. Just like with game item effect, we make a base class to define a consistent API. And now we can simply create as many different classes as we need for our different AI behaviors. The details are somewhat left up to you. But this is now very easy to extend. If our designers come up with a new AI behavior, we just add a new subclass of game AI, define any additional data we need, and code the logic. No other content or code needs to change. It's clean, and it's modular. I think you're starting to get the idea, so before everyone falls asleep, I will sum up. Scriptable objects are awesome. They put your data into different files to make version control easier. If you move a lot of data into scriptable objects, your scenes and your prefabs become faster to load because we've eliminated all the duplicate data in your files. They give your designers an easy and extensible workflow in the Unity editor. And you can use them to serialize the logic of your game, the flow of logic through your game. And then you configure it via content. So thank you. I appreciate that you've thank you for coming to this talk. I hope you've gotten some new ideas on how to use this very simple but very powerful little class. And I hope you've gotten some new ideas on how to apply it for your games. Thank you.